Okay, we are now live from downtown Mill Bay. How do we know we're downtown? Because that's uptown. Also, I'm going to try and use my new app. I can show you how it works. If I press on a name, actually no, it might show all the names, so I won't do that. It gives me, I press a button that says, give me a random person, and it will give me a, Charlotte?
What?
Are you Charlotte?
Yeah.
I think I marked you as absent. Did you just come in?
Yeah.
If you come in late, you have to tell me, otherwise later on your house parent will go, why were you absent from class? Excellent. There we go. So, out of all of you going to tell me what a mixture is Isaac. Isaac, what's a mixture?
Something I haven't already.
Oh, it's not written down. We were just sort of doing it last day.
Like that is the list was under mixture.
No, how would you define a mixture?
Liquid.
Could you have, so we got mixtures in here that are liquids. So milk is a mixture, coconut water is a mixture, but also concrete's a type of mixture. So is a butterfly, so is a window frame. So they're not all liquids, but what do they have in common?
They're not chemically
Good.
combined.
Your name's not Isaac. However, people near Isaac can help Isaac.
Yeah, they're not chemically bonded.
Oh, that's a good one. Excellent. Well done, Isaac. They're not chemically bonded. That's true. True. And that kind of does it. I mean, we've got compounds here, chemically bonded. We've got elements there. Oh, wait. Elements are also not chemically bonded. They just are. So that's very close. If you added a couple words to that, I actually probably could have worked. So I'll probably take it. Not chemically bonded, because we can build off of that. And contain if you add in contains different atoms, then you can exclude the elements from your definition, and then it'll work. Aha. I use this once in a while. It records every time you answer a question, you get a point. So right now, Isaac, you're winning.
It's like class dojo.
Yeah, it's class dojo. It's made for kindergartners. Like when you do like a good, you share in class, you give someone a point. I just use it for questions in the random feature. But also, if you're like away for a week, or I've been asking questions and like I somehow never ask you, it'll show me on points like, oh wait, this person never asks a question. Maybe I should ask them more questions. Or you're away for a while and then you just didn't get to, so we can catch you up. And make it a little fair so it's not always the person putting up their hand every single time. We can check in on what people know and how they're doing. So, mixtures. Not chemically bonded together. They're kind of loose solutions. So you've got lots of different properties all mixed together. So then how do we define a pure substance? Guy. Oh, it's not defined yet. You just have to go based on what we've already done. Yeah, it's not written down. Go with your gut. Pardon?
Is it an element?
Elements are pure substances. And down the bottom, elements are pure substances and compounds are pure substances. None of the mixtures are pure substances. So we have mixtures and pure substances. So you can get pure salt. But all the vodka, and it's always the same no matter where you are in the world. But if you get vodka from one store and you get vodka from another store, there could be differences. They could have different concentrations. If you have coconut water from one place and another place, they could be differences. So they don't have that similarity to them. What could we say? How could we define that in a way that would be easy to remember?
It can't be like separated into different things.
That's a very practical definitions. You can separate compounds, but you'd have to use chemical means. So if we work on it and say, cannot be separated except by chemical means. That's not a bad, that's a good one. So these we can separate. That's a terrible, terrible handwriting for separate. See what a text recognizes that. Excellent. Separate. Physical means. Pure substances you would need to separate by chemical means. We'd have to like rip the water apart. What about their properties? What would we expect from the properties of pure substances versus the properties of mixtures? Yes?
Pure substances are always the same, like no matter what you get, it's the same.
Yeah. Rather than writing it on there and scrolling all over, I will write it up here. Pure substance. Properties. Always the same. And mixture. Properties can be different. I'm going to double check that we're actually recording. I heard a little tiny beep. Yep, we did. Okay, I think that does it for that page. Anybody still getting anything down?
What does the properties of mixtures say?
Which one?
In the orange?
In the orange?
Yeah.
Here?
Yeah.
Properties can be different. Let's see if we can text recognize that. I'm not. Ooh. I'm actually impressed with it now. Property's always the same. Nope. We got some instead of same. Got close. Okay. How many types of atom do we have in an element? Yep. One. Just one type of atom in every type of element. Ooh. Atoms are made up of 3 subatomic particles. Everybody? Everybody did it in a different order. It wasn't like ominous enough. So we'll go M, N, E. So let's do an alphabetical order. Electrons, neutrons, and protons. So say it, electrons, neutrons, and protons. What are the 3 subatomic particles?
Electrons, neutrons, protons.
Excellent. If someone was walking by and they heard that chant, it would sound vaguely ominous. We are learning rote things. No, I forgot my alphabetical order. Oh, I think I still got it wrong. You chanted it and I still did it wrong. A neutron is basically an electron and a proton squished together. That's how you make them. If you have a radioactive substance and it gives up an electron, it's usually because a neutron spat one out and it became a proton, and a tiny bit of mass disappeared, and that's where the energy comes from. Oh right, I'm not supposed to tell you about that. Sorry, secret knowledge. What are the tiny dense ones? Really heavy, small. Neutrons. Other? What's the other really heavy one? Don't answer out loud, I'll pick someone again. Ooh, boom. Sterling.
Protons.
Protons. Electrons are diffuse clouds. They're sort of smeared all over the place. Where did I have the Did I do the diagram for that one? Oh, I'll do it next. So which one of those defines an atom and says, if you know this one, you know exactly what type of element it is? I will ask Aria.
Sorry, I wasn't listening. What?
Which one of those, protons, neutrons, or electrons, defines what an atom is? Defines which element it is? Protons. I got in a very silly argument with a university professor in third year over this. I'll tell you about it in a second. What subatomic particle do the protons determine? Neutrons or electrons? Louder?
Electron.
Why?
Because protons are positive charged and electrons are negative charged.
Fantastic. Protons are positively charged, electrons are negatively charged. And it's the electrons that do all the chemistry. And the electrons run around, and how many electrons you have left, how many electrons you need to gain, all of that is what determines the chemistry and the properties of the element. So the silly argument I got into was like, the professor said, there was some silly quiz where he said, which subatomic particle determines all the properties of the atom? And he said it was the electrons. And I said it's the protons, because they determine the number of electrons. And we had like is this a sandwich type of argument we do with burritos? Which really you're just playing around with definitions at that point. Protons determine the number of electrons. If you know the number of protons, then you know the number of electrons, and that's what you're going to do. But theoretically, if you could make an atom without protons, but just mimic the number of electrons, you could get it to do anything you want. And the electron cloud. Electron cloud is also known as shells, and we'll also call them levels. And I'm going to show you what that really looks like in a moment, because classically, I'm going to guess that when you drew, I've got a proton here, put a circle around it, and in previous, you would have, done that for your electrons in a Bohr model or something. It looks vaguely familiar. If I was to draw that electron according to what it is supposed to really look like, it's not orbiting like a planet around the sun. In the models, they just use what is the statistical likelihood that electron will be here at this time. So they usually represent it as a dot pattern to show the difference of the apparent likelihood. So when you see a heavy concentration of dots or smearing, it's a really high chance that electron's going to be there. And if it's fainter, there's a really low chance that electron is going to be there. So that's what we mean by the electron cloud. It looks like a cloud. And in the old Bohr model, which is what we're learning, that electron's in one discrete spot. But in the modern model, it's not in that discrete spot. It's in all these spots simultaneously. You can calculate the odds that that electron is going to be a light year away. It's small, but the odds are there. And so you just get a probability pattern. Now, it still looks a lot like the Bohr model, which is why the Bohr model still works for a lot of things. And the Bohr model actually simplifies a lot of stuff that you don't need to worry about when you're doing chemistry. So you can actually make a lot of predictions with it faster than if you use this method, which is why we still use it. It's fantastic. All models are lies. They're just lies that have different amounts of use. But this is just one particular energy level. If I heated this atom up, and I took that electron and I got really excited, it became another energy level, you would get a pattern. Let me use a different color. You get a pattern that looks like this. How many of you have seen this pattern before? Maybe have done some chemistry in Germany. No? No? How many electrons are in this particular model? One. It's smeared across two lobes. And that is called the P subshell. It's quantum. You'll learn about that in Chem 11 if you take Chem 11. It can fit up to 2, and there's 3 different ones. And so there's a probability, and there's still a probability, you'll find out here, but the highest density is there. So they actually look physically different. That changes how they bond, which is why you'll see the term electron cloud. And I'm telling you all of that so you can know, never do that, because we're not doing that. We're going to pretend they're little planets going around the sun, and that's how we're going to draw them. It's going to make a lot of things easier. But in the back of your mind, you can know that they're different. I would like you to draw your Bohr model of lithium that you would have drawn last year if I said protons, neutrons, and electrons. But before you do that, you 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I forgot where I started counting. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Excellent. We're an even number of people, which means grab a partner, get a whiteboard pen, and I want you to draw your model on the board so I can see them all at the same time. Draw it, get together with a partner, and then once you've drawn it, you can sit back down. Yep, right now. There's lots of whiteboard pens over there. There's a whole box of them here. Someone stole my other box of them, but we have enough. You've been sitting down and listening to me long enough, you can get up.
Let's go.
So 6.9. There's 4 neutrons. Because you would subtract the amount of protons from the atomic mass. They never come off. So, 3 protons. Right, Ella.
But just 3 protons.
I do apologize for the squishiness. Asked for more whiteboards in here, but we don't have them yet. Oh yeah, who's your partner? Who doesn't have a partner? Someone must also not have a partner. Do you have a partner? Pardon? No, because we have an exactly even number of people. So if there's a trio, then we'll have someone out. Work with Artie? Oh, you don't have to argue. You just draw your model, and then you sit down. Sit down. You don't have to argue with other people over your model.
No, that was my.
Then you do have to argue because you have to agree on something. Fair enough. Yeah.
There we go. Do you not remember talking to neutrons?
Oh, they didn't teach me that. I was told that the number of protons and neutrons are the same.
Oh, shit. We made a mistake.
If you leave it though, then I get to comment on it.
I just find it.
And nobody knows it's yours.
Should I leave?
Yeah, because they're gonna go through them all and see what mistakes there are, and ask you how you knew such darn things.
Well, I'm kidding. I'm kidding. I'm kidding.
Dun, 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 dun.
Kidding, kids.
Actually, all drew very similar models,
Yeah.
and there's no Germans in this class. Ooh, one drew a clever one. Nice. Okay. Now it seems like eventually everybody figured out there was 4 neutrons. How did you know that?
Him.
You from him? Did you supply the entire
Yes.
class or just the part? Okay. How did you know?
I used to check the amount of protons from the atomic mass.
What's the atomic mass of lithium from your periodic table?
6.1.
So you took 6.9 and you minused 3 and you got 4?
Yeah. Well, because you round.
Oh, because you round. So you actually got 3.9. That is the clever thing to do. You round to 4. Why do you round to 4? Why can't you have 3.9?
Because electrons have, like, effective mass, like, every other.
Nope. That's a good guess. Electrons are incredibly light. Worrying about the mass of electrons is like worrying about if a big truck is getting weighed for the amount of I don't know load in the back. It's carrying garbage, and you weigh the truck. Worrying about electrons is worrying about the flies landing and taking off. Their mass is so small compared to the other things. Yep.
Is it like the average mass?
6.9 is the 6.9 is the average. So yes, it is an average, and no atom exists that has 6.9. But why does no atom exist? Because you have 6.9. There.
Well, because there's always like certain amounts of protons and neutrons in the nucleus, but like there's different isotopes with different amount of neutrons.
Right. And when you said certain amounts, I know what you're getting at. But can you clarify? What do you mean by certain amounts? How many neutrons is it possible to have?
It depends on like the.
What numbers are forbidden to have? Like what number of neutrons can't you have?
I think like I don't know.
I think you know. I've just asked it probably in a confusing way. Can you have 6.9 neutrons? Why not?
It has to be like a solid.
It has to be a solid. I like that. A solid number.
An integer.
An integer. And you can't have negative neutrons, obviously. And to put it in another context, there are, on average, last time I checked, there were in Canada families that have children. The average number of children in each family is 2.3. I think that's gone down in the last 10 years or so. That was the last stat I read. Can you ever have 0.3 of a child? No. I mean, even if they've lost an arm and a leg, and they're like, oh, they are still a whole person. We don't discriminate against people just because they're missing mass. They're still a whole person. So you can only have 2 or 3 children. You can't have 0.3 of a person. And same with neutrons. They are either there or they're not there. You can't have half of one. So the 6.9 is an average. You round it. In some cases, that means you may be making an impossible atom. There are atoms whose isotopes are things like one is 22 neutrons and the other one's 24. The average comes, because they have 50 of each, the average comes out to 23. But in real life, no isotope with 23 neutrons actually exists. And there's a few cases like that. So always know it's an average if you're ever given a number of neutrons. So 2.3 children per household is a useful stat for Canada to know. If we're going to do some new child benefit, then they will just go, oh, we will multiply by 2.3 times the number of families times the benefit. We'll know how much this costs. But if you know that we're talking about Fred's family and they've got 7 children, then we know, no, we have to actually provide for 7. So sometimes we're going to tell you that, and sometimes we're going to give you the average. The average is the atomic mass. Does anybody know what the specific amount is called? Not the average mass, but the very specific mass. We're going to get to it in the notes, and don't worry, we'll do it. So the only reason I have this, I don't like the word better because this isn't better. I'm going to put, I was going to put efficient. That'll work. So everybody drew it like this. So last year you would have said, and I don't care if the 3's in front or behind. I tend to do this because I like putting the charge. It reminds me that protons are positive. 4 neutrons, and I usually put a 0 there, but exactly the way you did it there, it looks like how everybody was taught in grade 9. That's absolutely fine. Put the circle around. I'm just drawing what seems to be the average of yours. And then most people seem to do a ring. And another ring. And then most people did this. And this. And then like that for our 3. Now, did anybody do something different? Oh. This one, put 1 and then 2 apart. And that wouldn't happen. You can think of the atom as existing at the bottom of a well. All the electrons fall down to fill up all the space like marbles. And so if there's a free spot, it will move down and you'll get 2 and then 1. So they fill from the, does anybody remember the number that fit in the first one? How many fit in the first one?
2.
How many in the next one?
8.
How many in the next one?
8.
Next one?
8. 16, right?
I want you to take out your periodic table. And turn to any periodic table that looks like this. I'm going to get my periodic table up. I'm wishing I could point to it, but I'm still not at that point. I think it's sitting right over there. But they're going to put whiteboards in, and I don't want to put it where they're. So everybody got one of these? How many atoms? How many types of elements in the first row?
2.
2. How many in the second row? Hey. How many in the third row? Hey. And now count. How many in the fourth row? Don't point to numbers. Let people count. How many? 18. So if you ever forget the number of electrons, it's actually duplicated on your periodic table. Because your periodic table, does anybody know why it's called a periodic table?
Because it's measured in periods.
These are called periods. Why are they called periods? What does the word periodic mean?
Organized.
It's organized, which is true. It's organized in a particular way. What other things are periodic?
Different like times or stages.
Different times or stages. I mean, there's a famous one that we actually just use the word for as well in the menstrual cycle because it happens over a month and it keeps happening. This one also keeps happening, but it keeps happening with, if I start with lithium, explodes in water, plus 1 charge. Beryllium doesn't explode in water as much, but does react, plus 2 charge. Boron, plus 3 charge, has some metal properties. Carbon, plus 4 charge or minus charge. Nitrogen gas, minus 3, minus 2, minus 1, and then a noble gas. And then we whip back down to sodium, and we have something that's plus 1 and explodes in water. And so every time we do that, we whip back, we find something where its properties repeat. And so there's this repeating cycle of properties. And that's how we organized it to begin with. With Mendeleev in Russia had basically what looked like a stack of playing cards where he put all the properties of the elements. And then he just put things in families. This is before he knew the number of protons. Nobody knew subatomic properties. And he got it basically right. Because based on properties, you can see this repeating pattern. They repeat periodically. Hold it, why did I start this conversation? And then I went there, and then I said, and then I went, what was the question I was asking?
Or is it called the periodic table?
About the.
Yeah, but before that.
About electron numbers. And then the.
Oh, right. And so that is why the periodic table reflects the number of electrons, because the number of electrons reflect the properties. And so it just so happens, if you put things in the right properties, they end up with the same number of the same number of electrons. And so you can actually, that just naturally gives you the electron level in each row. So even before they knew the structure of the atom, they theoretically could have predicted it just from the shape of the periodic table. By the way, this is not the only shape. There are a ton of different periodic tables out there that use that when they make it in different orders, it actually shows new information about how you can see what the properties are. There's spiral versions, all sorts of cool things. Yep. Yes. Oh, I didn't do this in this class. If you have to go to the washroom, I haven't started taking phones yet. We're supposed to get a box and do that, and I keep forgetting that I don't have the box. Just don't even ask. Put your phone on the back table. Head to the washroom. If you're going to be gone for longer than a reasonable washroom break, like, I don't know, you're going to go and talk to Mr. Rodriguez, visit other teachers, be gone for 45 minutes, you have to let me know first. But if you just go in the washroom, you don't have to ask. Okay, so that's how you've been drawing it. It's perfectly fine. It's big, and it's inefficient. And there's times I'm going to ask you to draw a lot of them. So what I would like you to draw them like is this. If you have to put in all the things, you can still do the same things. You could put in your numbers, but you don't draw a circle around it. And then you would go, and then sometimes we do this, just to indicate, that indicates, oh, this is actually a whole orbital, but we don't draw it because that takes up a lot of space. And if we're being really compact, I might, if the neutrons isn't important, and sometimes it isn't, we might just go 3p, 2, 1. So that's our regular Bohr model. That's our compact Bohr model. The electrons, the E is assumed. You know where electrons are. Why would you have to write E every single time? By writing P there, we know that's the protons, we know that's the nucleus, we could put it there. We really want to write in the neutrons, because it was important we could. You can write either one. I almost always put the E in, because I'm slow, and sometimes I forget where the electrons actually are. But theoretically, I do have a degree in chemistry. I should know. Okay, so this whole thing is just to transition you from grade 9 meta, is science and meta? Yeah, okay, and get you into like gearing towards senior chemistry, writing things in a shorter fashion. Fill out the table. What is the symbol, charge, mass, and location of each of the subatomic particles? And then I will use my magic button and ask you all questions once you've confirmed what the answer is.
For location, do we just write like shells or nucleus?
Yes. You write down where you think it is.
Yeah.
Shells is perfectly reasonable. That's the spot in the nucleus. Not in the nucleus, in an atom. And anybody leave this behind? There's no nucleus. No. Yeah. Nucleus, shells, cloud, bubbles. Where did my pen go? Who drew this one? Nicely clever. Why'd you do that?
Just have it.
I know, but why? Everybody else drew them apart. You drew them together.
Yeah.
There was 2 in the first shell, 1 in the next shell. What if I told you to put 5 in that outer shell? How would you draw that?
Like together, like 1, 2, 3, 4, 5.
So you'd go like this.
1,
they may have not have done it for the first one, but how many of you would have done that if it was 5? How many of you would have drawn it, say, evenly spaced around? Well, only about half of you said you'd do it the other way. So the other half of you are either lying or have some weird other pattern. Congratulations, you have a, if you did draw it, like that, where they're paired, first shell is paired, you start pairing them after 4, you already have a head start on Lewis dot diagrams. So whoever taught you that taught you well. Excellent job. And if you didn't, we're going to do it, so you don't have to worry about it. But that's a very Lewis dot diagram way to do it. Were you in Meta?
Yes.
Oh, and they taught you that?
Oh no. Yeah, maybe.
But nobody else did. Who'd you have for your teacher in Meta?
Accountant.
Oh, excellent. Okay. That means I need to go give the smackdown to like Mr. Doler. That means Miss Chung's teaching it properly. Excellent. Everybody done? Oh, sorry, asked that the wrong way. Anybody need a couple more minutes? Excellent. Kiona, pick a random box. Tell me what it is.
Charge on electron negative.
And Eric.
Charge of protons is like
Yeah, in fact, and when I call, given how I realize how easy these are, and I ask for the whole column, what's the charge on a neutron?
Me too.
Pardon?
Me too?
Yeah.
It's neutral, so it's not.
So it's nothing. And next one, pick a column. Tyler.
Oh, the symbol
Okay.
E P N.
Often, especially for electrons, we include the charge. If you forget, often we don't for the protons. We almost always do for the electrons. Why, does anybody know why we almost always put the charge in for the electrons? How many of you heard of E in math? There's a whole other E. And so that's just to distinguish it in case someone was so confused they thought you meant E from math. Jessica.
Location of a new electron is the shell.
Electrons, the shell. Keep going.
Okay.
Wrong table. Whatever.
I never made that mistake. And you
then
cannot prove it.
The location of a proton or neutron is the nucleus.
Nucleus.
We can't prove it, it's on the live stream.
Oh, right, it's on the live stream. And Tom, mass.
Proton, the mass is 1. Neutron also. And electron, I learned in Germany it's 8.00 times 10 minus 23 on the top, yeah. But I think it's a different unit and not mu. So
Oh no, that's it in like grams or something.
yeah.
Yeah. So
Because I never heard
Yeah.
the unit mu or
AMU?
Yeah.
AMU, the mass of one proton is 1 AMU.
Oh, alright.
The one of one neutron is 1 AMU. And the reason that number becomes important later on, I want you to cross that out, and we're going to write in approximately 0. Because, and I love that you know that number because now I can show why we do that. Where's my? This is a great addition for sig figs later on. Did they teach you sig figs in Germany? Do you do sig figs in grade 9?
Significant figures.
Significant figures? No. Okay.
I don't know actually.
No, I'm just trying to figure out in different areas. So we have something that weighs. That's in grams. I am going to convert that to AMUs. 1 second. I do need my calculator before it. It is roughly, I'll do a quick and dirty calculation. So that number is approximately 0.000625 AMUs. So if I say have an atom and it has, we'll use this one, we have 3 protons, so it weighs 3 AMUs. And we have 4 neutrons, so it weighs 4 AMUs. How many electrons do we have? 3. So that times 3, 0.000625 times 3 equals 0.001875. So 3 electrons equals 0.001875 AMUs, which equals to 7.001875 AMUs. So what is the mass? It's 7. Because we don't care about that. Because it's too small. Who cares? Pshaw. We're only going to worry about that. And some of the variations in our measuring, like when you measure the mass of things, your instruments can basically only get to there. So this is within experimental like error. So we just ignore it. Now there are cases where you can't ignore it. We're not going to worry about those cases. So that's why we say it's approximately 0. So unlike light, electrons do have mass. We just pretend they don't. We're just doing it. Next year, maybe this year if we have time, you're going to learn a little bit about this number. And that's a special number because if you have enough of them, if you have 6, 1, 2, 3, 4, 5, 6, 7, 8, 9, 12, 13, 14, 15, 18, 19, 20, 21, 22, 23. AMUs, you have 1 gram. So that's the mass conversion. So if you count out that many atoms, protons, you'd have that many atoms. But it makes it really easy then, because if you have oxygen has how many AMUs? On your periodic table, what's its mass? Periodic table, not 2. Yeah? 16. So oxygen is 16 AMUs. So if we had something like water, H2O, if I have that, what does hydrogen weigh? 1, and I've got 2 of them, plus the 16 for oxygen, what would that be in AMUs? 18 AMUs. And you're like, okay, that's still a really small weight because I need that many of them. But now, I could say, wait a minute, if I weigh out 18 grams of water, exactly, I just weigh out 18 grams, then I know I have 602200000. I'm just going to put a side notation. 0.622 times 10 to the 23rd molecules. And now, with a mass balance, like get on a scale and you measure the mass and you know the number of atoms. That was a huge breakthrough because now we can count atoms with scales. We don't need to individually count them with demons, and that allows us now to do some really interesting chemistry because now we can actually figure out how much of stuff is in stuff. Write down what all those numbers are. I don't want to be too... I put snowium because I think it would be a little too forward to put Neufeldium. But you do know, I hope, that if you ever go into chemistry, that is a long-standing tradition that if you discover an element, you name it after your grade 10 chemistry teacher. So someday I'm hoping for a Neufeldium. It's just, you should just do it automatically. Don't even think about it. If you ever make a great discovery, and you're a little worried that people are going to take advantage of you, just remember, come back, show it to me. I'll help you. And you'll get everything you deserve. There'll be people out there that try to take advantage of you. Mm-hmm. 3, 2, 1. Cheng Chow. Top to bottom, what are these? proton number. That is actually what it is. And what do we call the proton number? Atomic number. Perfect. And this next one, because I'm going to say a little something about each one. Alexander,
Atomic symbol.
atomic symbol. And what do we notice if you look at the atomic symbols? Anything you can notice about them? Any repeating thing that is, yes?
The first letters in the capital,
Yep.
whatever comes after.
And that one's lowercase. And the reason I'm being pedantic about this, like, who cares? Okay. It's because if you write this, that's cobalt. And if you write this, that's carbon monoxide. And if you write this, that's still carbon monoxide. It's just small because it's both in lowercase. I don't know what it is. So you have to be careful. If I've seen people just out of habit, they capitalize everything because that's just the way they write. You can't do that with elements. You have to be precise in what is uppercase and lowercase. It's not even like bigger or smaller. If you have an element, for example, that was this, great. But if you wrote this, it's now lowercase, but written big, like uppercase, lowercase. Anybody know where the words uppercase and lowercase come from? Old printing presses, you would have to actually take physical metal pieces and put them in your printing press, and they go chunk chunk to print your newspaper. And you use lowercase letters most of the time, so they were on the lower case, lower to your hands for putting it in. And then whenever you needed a larger one, you would move to the uppercase where all the capital letters were. And all of our language is reflecting old machines that no longer exist. The size of our highways and how big we have to build our rockets is based on the width of a mule's butt. Because that's what determined how wide the train tracks had to be, because that's the trails that were already there. And then when they built the trains tracks, they did it on an average size of that was there because it was easiest to build. So then when they designed the rockets, they had to go on a train that have tunnels that limits its size based on train tracks we've already made that were based on mule tracks and became standardized throughout the world. Our whole world is filled with old measurements that we no longer need, but we just built our society on them. This is obviously the name. And we already did this one. That is the atomic mass. Okay. Neutral atoms. What two things are equal to each other? Protons and neutrons. So put them in the correct location. And what is the charge of a neutral atom?
0.
Sure. So have 0 overall charge. As a call out, which one's negative? Electrons. Which one's positive? Protons. Excellent. Atomic number has to be a whole number. This is one of those counting things. You can't have half a proton. You've done something bad at that point and split it up into subatomic ones. We already know it counts the protons, so we're going to whip through that. All atoms of the same element have the same number of atomic number of protons. Yes. Now, here's the magic word. I asked earlier, do you know the name that's not atomic mass that refers to a specific element? And it's called the mass number. The mass number is equal to the number of protons plus the number of neutrons for a specific atom. So it's the mass of the nucleus. You can't find the mass number on the periodic table. You only find it when I tell it to you. So for example, if I asked you for carbon, what is the number of neutrons in carbon from your periodic table? Yep. 6. And how many protons does it have? 6. If we write the number of protons on this symbol, does anybody know where we write it? You write it right down here. You write 6 there. If it has a charge, you write it up here. We often don't write the charge if it's 0. But if, for example, if this happened to have, I want the eraser, happened to have a charge, we would write it right there. And then here, we write the mass number. So that's carbon 12. But I did extensive work with carbon 13. How many neutrons does carbon 13 have? 7. There's a small amount of carbon 13 in amongst regular carbon. You could do NMR and a variety of really cool sort of nuclear magnetic resonance imaging. That's just MRIs for atoms. We call MRIs and not NMR. It's all nuclear magnetic imaging, and by nuclear we mean we're using properties of the nucleus. And specifically, these isotopes have a particular property we can exploit to detect when they're there. And people didn't like the word nuclear because they thought it meant it was radioactive, so we had to call them MRIs and hide the word nuclear so that people didn't freak out when they went into one. It's literally the only reason why the name is different, and I have to tell you that. I just realized I forgot. Oh, that's also a whole number. So that's for an actual atom. I have had samples of pure heavy water that has been very careful, so it only has one isotope of hydrogen in it, and actually tasted it. It should theoretically do nothing to you because if it's a different isotope, it has all the same properties. However, it does have a very slightly different mass. And the mass of water changes just enough that if you manage to just drink liters of it and replace all the water in your body with heavy water, I'll show you what heavy water is in a little bit, you would actually slow down the reactions in your body enough just because of the mass that you might get into real trouble. Someone volunteered to do it, and the scientists took him to a mental institute to get help, because you shouldn't volunteer for such things. Take your periodic table, either the colorful one or this one. And get out a pencil. Actually, use the one that's not colorful. Use this one. Use it. Get out a pencil. And between you and your partner, I want you to pick between 1 and 30 your favorite element. Circle it in pencil on your periodic table. What is your favorite element? Your favorite element. 1 and 30. You're not allowed circling, plutonium. You can't even circle, hold it, 1 and 30? Oh yeah, we could do 1 and 30. Actually, no, I'm going to leave off the inner transition metals. 1 and 20. Yeah, sorry. No titanium for you.
Why?
Okay, fine, you can keep it. If you really want it, you can. Everybody have one circled? Circled? Because you were like, no, good. Okay, great. The one you've picked is the one you have to draw on the board. Yeah, grab your partner, erase what's already there.
What's the difference between a mass number and an atomic?
So atomic number is the average. So like of every atom, what's the average? So for lithium, it's 6.9. But for the mass numbers for this atom,
For a
what is it?
specific one.
For a specific one. So for lithium, it is 7. But for another one, it might be 6. And put the symbol of the element above it so that I can check which one you're doing.
Right, 22 plus 26.
Mm-hmm.
We draw the Bohr model that we did.
I want you to draw it. Oh, the new Bohr model.
Oh,
The more efficient one. Erase what's already there. Grab a cloth. Don't use your hands. There should be cloths there. Clothes.
They can't hear.
Is that an eraser? Ooh. Did someone lose a pencil case? No name. Pencil case.
Wait. Yeah, 26.
Oh, no. Erase old ones. Oh, beautiful. Oh, we're doing well. Good. 20, 18. 16, 17, 18. Hold on. 18. We have 24, 8, 16, 20, 8, 16. Plus 4 is 20.
What? I did it wrong.
I think that one might have a mistake. 8 and 2 is 10, plus 1 is 11, good. 2, 4, 6, excellent. 8 and 8, 16. 17, 18, 19, good. 8 and 8, 16, 17, 18, 22, good. 16, 3 8s are 24, 25, 26, good. Iron, nice. 8 plus 4 is 12, good. 26, hold it. Someone drew it the old way. This is a good point. Now let's say I decide I'm marking something and I said draw these 20 Bohr models. And I've been marking and people have been drawing like this. Like oh, and it looks cute and it goes up like a ray. Like oh. And it's easy to read and like boom. And then I go to this one, well it's not as an array, but it's easy to read. Then I go to this one, it's easy to read. Then I go to this one, it's easy to read. Then I go to this one, it's easy to read. And then I get to this one, and I have to count. And I have to go 1, 2, 3, 4, 5, 6, 7, 8. It takes so long. But it's still correct. I'm going to mark it. But these ones, you know, I've got my blue pen out, or my purple pen, or my green pen, and I'm just marking away. I'm listening to music, I'm calm. Got a nice coffee. Then I get to this one. I put away my blue, green, and purple pen. Got a red pen. I turn off the music. I put away my coffee. And I feel very grumpy while I'm marking it. They still come out fine. Just gonna be more grumpy. Just to let you know. It's just really hard to mark. So 2, 2, 4, 6, 8, 2, 4, 6, 8. I think And then you spaced out these ones, which is highly problematic. But you don't know, so that's fine. One of the reasons you don't know, actually this is a good point, because you all know it's 2, 8, 8, 18, right? Except that's actually a lie. It's actually 2, 8, 18. And you'll see it in textbooks where it says 2, 8, 18. And then they expect you to do 2, 8, 8. And they never tell you why. And the reason for that is the energy levels are not 2, 8, 8. The energy levels are 2, and then a 2, 6. And then the next one's a 2, 6, 2, 6, 10. And then the next one's a 2, 6, 10. However, when you fill this one up, you get 2 electrons. When you fill that one up, you get 8 electrons. So from a Bohr model perspective, you see the same thing. And then, when you fill this one up, this one goes there. It just sort of drops and then sort of goes away. So you get that 8. And then this one fills the 2, and then it fills that 10, and then you get that 6. And so you get your 18, and that one goes to the next one. But it actually belongs to that one. It's quantum. It looks far better if I do it like this. That's 2 electrons. And the next one's. So 2 electrons, 2 in each spot, 6 electrons, so 8. And then the next level is so you see 2, 2, 6, so 8, then 2, 6, how many would be in here? 10, 5, so 1, 2, 3, 4, 5, 2 go in each one. But when the next one starts, it starts here. And then we get that, and so it goes and then it fills up here, and instead of going to its next energy level, this one's still left over from the old one. And you end up with that fine little detail and structure. And then once it's full, it actually drops down to where it's supposed to be, and then they come off in a different order. And that is why chemistry can be a little bit interesting, because it all depends on what the energy of the electrons have. So there's all these hidden things sort of built into the underlying structure of everything. Okay, those are all good. Erase them. Draw those 2 mystery atoms and answer those questions. Yes. Oh, and pick a brand new partner. You may not stick with the same person you've been sticking with. Oh, no. Sorry, right. Quantum. For your purposes, 288 is fine. 28818. Because we don't get to the fact that it's secret. We'll tell you next year chemistry. So, come up on the board, erase what's there. Brand new partner. Can't use your old partner. Are you able to walk without any crutches? Or are you just doing it and it hurts? Okay. Okay, you're allowed. Erase the old stuff. Erase the old stuff.
Okay.
If I stole a whiteboard and put it right here, and then put another one right there.
Okay. In the next time. Yeah, alright. Could you read me the yeah, the math number. Wait, 17? Good math. 8? No, correct. It's not 8. Wait, Adam, why is the same? Math number is 7. Oh, wait, I'm tripping.
You be tripping, yo.
Wait, they are different. They're the same Adam.
Once you have both drawn, make any conclusions about them. How are they saying? How are they different? Write them in point form. And have a seat.
How are they?
Do you have your erase them?
Okay, we have concluded that they're the same.
You would be waiting for the end of class.
Oh, okay. They're not different? Is that the point?
Yeah, I will. I don't know if it moved to the lab. Sometimes we have to. Like
Is the Y?
Is the Y.
What's your conclusion?
Once you've got them down, you can have a seat.
Well, you guys have to be there if you have an hour. Like an hour till 7. You have 1 hour to get ready. Like an hour till 7. Oh. There's always retakes. You know, people go to the very back. When is the like? No, I think it's like.
Oh, roll that. Safety. Okay, so task was here's two things: 9 protons, atomic number of 9, 8 neutrons, mass number 17. How are these the same and how are they different? Okay. Boom, drew them up, exact same. Boom, drew them up. They have no idea if they're the same or different. They wrote nothing. There's no conclusions that they can make. Also, no, nothing. Very nice drawing though. Same atom, identify them as being the same. Didn't erase old things, slightly confused, but I think this is it. No conclusions to be made. Same atom. What is that? Oh, that's an N, not a V. I need to put on my glasses. Also no conclusions. Beautiful atom, no conclusions. So, if you're asked the question, write down what your conclusions are. Part of your evaluation competency comes through. Now, you may think, but Mr. Neufeld, I drew them and they're obviously the same. I know that. But I don't know that you know that. You have to tell me you know that. And then I can actually make that determination. Because there have been people who don't know that, even though they look the exact same. And I never quite know how much to go into. You have a summary sheet. So this is essentially everything that you should have known from grade 9. So if you need to refer to it, There is 288. We don't actually really go beyond this. So I've told you about 18, and someone was like, do we have to know it's 18? No, that's all you have to know. We're not going to go back. We don't tend to go often past element 20. You could, now that I've shown you how to count it, but you don't have to. We already drew it. We did that. Now we're going to talk about isotopes. Isotopes have the same number of protons, but a different number of neutrons. So rather than hold it, they have a different number of neutrons. They are the same element. And this is where we have things like heavy water. So if you have a nuclear power plant and you want to safely shield everything, one of a really useful ways of doing it is covering the stuff you're trying to shield with enough water. Because water, although the hydrogen is light, the oxygen's got about 16, so there's a bit of a nucleus there. And you can make it a little heavier by adding some deuterium. So we actually give this one a special name. The atomic mass of hydrogen is basically 1. It's 1.0001 something, I think. So most of the universe is made of hydrogen. How many neutrons does one hydrogen have? 0. And so if I was to draw a hydrogen plus 1 atom, what would I draw? What would I need? If I have H plus, what would I draw? No electrons. It's this. That's called, this is a naked proton. It is the only subatomic particle that you kind of can, like, you don't ever find lone neutrons. You find lone electrons flying around, but they're, again, light. They don't really matter. But you can get, like, this mass, dense, heavy nucleus, strip it of its electrons, and get that naked proton. That's what acid is, and that's why acid can attack things so well. It's got a whole +1 charge on that tiny little space. Now, if we give it another neutron, we got deuterium. Does anybody know what 3 hydrogen's called? We got 2 neutrons. 3 times heavier. Tritium. I did drink about a gram of deuterium water. At a lab I was working, they had access to it, and he said, like, it's a rite of passage. Everybody has to do this. In retrospect, perhaps I shouldn't have. But there's the head lab guy. And it's interesting because it tasted exactly like water, and I couldn't tell the difference. Now, I've shown you how to write the mass number already, where you put it up here. That's the mass number. That's the atomic number. But another way of writing it would be where we write it and the -1. So this is hydrogen 1, hydrogen 2, hydrogen 3. Or uranium 238, or uranium 235. Does anybody know which is the one that's dangerous? 235. That's the one that we use in our power plants, and that's the one that we can use to make bombs out of. It's very difficult. It's really easy to make an atomic bomb, by the way. Like you could do it. They once paid a grade 11 student as a summer project. Like literally a scientific group, university came and said, hey, we're hiring grade 11 students. A bunch of grade 11 students applied for the summer project. We want you to build a nuclear weapon. Just go out, use the internet, use public libraries, get information, build a working model on paper, not a real model. And all of them were able to come up with something that would work. It may have, destroyed the person setting it off. They weren't very good at getting remote detonation because that requires more knowledge. But all you need to do to make an atomic weapon is have some uranium-235 in one hand, take some uranium-235 in your other hand, and clap your hands. If they get near each other, if you have what's above what's called critical mass, it explodes. So all you need is a cylinder or any device that has less than critical mass, and then another piece that fits in it that will take it over critical mass and just keep them apart. And when you want to make them go bang, just put them together. That's all it is. It's really easy. The hard part is separating these two. because most of uranium is 238. So you need to get pure 235. They are chemically identical. How would you separate?
Is that illegal?
Pardon?
Is that illegal?
To separate them? I'm sure there's many governments in the world that would have a dim view of it, but like Canada does it all the time. We're one of the major exporters of uranium. We have lots of uranium. Again, Canada is not a country. We're just a bunch of mining companies and resource lumber companies disguised as a country.
How big would the blast be?
Well, I mean, if you're good at making it. I mean, the ones that they built varied from taking out a chunk of a city to like a few blocks, depending on the efficiency. But they could make a pretty big explosion, and they were definitely all dirty. They would make radioactive everything. But what's the only thing you have left to separate these two? There's only one property they differ by. I can't hear you talk. What'd you say? Louder. Neutrons? You can't touch the neutrons. Well, what are the neutrons affecting? What is this? Mass. So you can separate them by mass. This one's very slightly lighter. Anybody know how you separate things by mass? Spin them really fast. Have you like panning for gold? That is a really difficult process if they only differ by a few percent. So the ways that the countries try and control this production is caring about who has the ability to buy centrifuges or things that can spin. Next day, you're going to do a little bit of work. You'll have a quiz next week based on the material we do this week, just to give you a heads up. So we've got some practice work coming up. So this has all been sort of background. Hopefully most of it's been familiar from grade 9. And your lab. Please put it on the other labs right here.
Can we try adding on this?
Write it down, yes. It should also be on every page, but I really appreciate it. You should have it on the outside of the classes
Let me borrow a pen.
and everything else.
Let me borrow a pen.
Pardon? Yeah, and when you got. Right there, on top of the other purple one.
Yes, assembly.
Wait, serious? Oh yeah, there's.
Do we get cookie?
Yeah, it's cookie breaking and assembly. What time's assembly?
10th and 9th.
Yes, and by that point you have to be seated in assembly.
9th.
What was? Yeah. Oh. Are you gonna shoot? Oh. You just had to write. You got the reservation lab. Oh.
I did that.
Thanks for that. Invisible, I haven't done this in broken, but no, for some reason I haven't I think the only other thing was that I also asked, like, if you were to do it again, how would you change the procedures to testing this question? Okay, good. And that was the homework. People worked on it, added to the discussion at home. Okay. Is your name in it somewhere?